Start now.
Good afternoon, everyone. My name is Junpeng, a master's student at Fudan University, and it's my pleasure to give this presentation. Our work is MeshUp Stateless Cache Side Channel Attack on CPU Mesh. This is a joint work by Fudan University and UCI. Let's introduce the background briefly. One of the important causes of cache timing attacks is hardware resource sharing, such as cache, MMU, TLB, buses, CPU execution ports, cache directory, and CPU interconnect. MeshUp is also based on hardware resource sharing. Our target is CPU interconnect. The typical intra-CPU interconnects are ring bus and mesh. Ring bus is efficient when there is only several cores, which is common in customer CPUs. However, as the number of cores increases, the ring's bandwidth is not enough, and the communication latency between two cores is also too high. A mesh networking topology will mitigate these issues. So mesh is common in server-grade CPUs, which usually have many cores. The workload ring investigated the side channel issue of the ring bus. Our work focuses on mesh. As the picture shows, sometimes different CPU sockets need to work cooperatively. On Intel's platform, this interconnect is called UPI, Intel UltraPath, which is also our target. The picture in the left is an Intel 28-core Skylake SP CPU chip. There are many types of tiles, like core, UPI, PCIe, and RMC. All the tiles are connected by a mesh network. Our experiment platform is similar. However, 4 tiles are disabled. The picture in the right is my simplified mesh network, and I will introduce our work based on this picture. The route policy of mesh is XY route or YX route. Data and control flow goes vertically firstly and then horizontally. Each tile contains a core part and an anchor part. The core part contains ALU registers, control unit, L1, L2 cache, and so on. The anchor part contains CHA, LLC, cache directory, and so on. Here is the cache structure with mesh interconnects. Take our experiment platform Skylake SP, for example. The L1 and L2 cache is private, while the LLC is shared by all the cores. As the picture shows, green cache lines in tile A's L2 cache could also appear in tile B's LLC cache. The L1 and L2 cache is inclusive, while the LLC cache is non-inclusive. In other words, all cache lines in L1 must occur in L2, but cache lines in L2 don't need to occur in LLC. As the picture shows, tile B's L2 cache contains 6 orange cache lines. However, there are 5 orange cache lines in all the LLC slices. The CHA of the anchor component is responsible to maintain states and positions of cache lines in L2 and LLC cache. A hash algorithm maps one physical address to one CHA. More details could be found from our paper. Based on the background, we designed a new cache side channel attack, MeshUp. Here is our third model. MeshUp could conduct cache side channel attacks on 2 levels, cross-core level and cross-CPU level. As a picture, for cross-core attack, attacker and victim reside on the same CPU but on different cores. For cross-CPU attack, attacker controls at least one core on each CPU connected by UPI. In these 2 scenarios, the victim will introduce some data flow on the interconnects like accessing memory. This assumption is common in the cloud, where lots of virtual machines and containers are deployed on different cores and CPUs. Our attack strategy is to monitor the data flow related to victim on interconnects, including mesh and UPI, and then we aim for victims' memory access patterns. Unlike traditional cache attacks relying on the timing difference between cache hit and cache miss, Our attack exploits timing difference resulting from interconnect congestion. The attack procedure is quite straightforward. The first step is probe and the second is infer. In the probe step, like pseudocode, the attacker accesses the remote data ceaselessly to make congestion, and then she records all the time between two operations. In the infer step, if there is no extra data flow in the interconnect, the latency will be stable and relatively lower. If attacker observes higher latency, it means that data from other sources is transmitting. Our cross-core and cross-CPU attack use a similar attack procedure. The difference is in how to access data. Let me introduce cross-core attack firstly. Let's assume that attacker controls tile A and victim controls tile C. Victim has a noticeable memory access. The key point of our probe is to generate high bandwidth to contend with victim. The probe also needs a high frequency to achieve a high resolution. Cross-core probe is based on Cacheline evictions. Firstly, we access several eviction sets, which is a set of Cachelines. By accessing this eviction set, we could force match flow between two tiles. Then we record TSC time drive by the instruction RDT at CP. The eviction set should contain Cachelines that locate in one tile A's L2 set. They should also locate in tile B's LLC slice. This table shows the mapping between physical address and cache. We could see that bits 15 to 6 are L2 and LLC set index. However, bit 16 is only LLC set index. In other words, one L2 set corresponds to two LLC sets, as the picture shows. Now about the eviction set size. We assume WL2 is the width of one L2 set. WLC is the width of one LLC set. If EV size is less than WL2, Cachelines will not be evicted to LLC. No congestion will occur. If EV size is larger than WL2 plus 2 WLC, some Cachelines will be evicted to memory. The probe frequency will be reduced. In summary, the EV size should be between these two values. Now, how to construct an eviction set. Firstly, to make sure eviction set locates in one tile A's L2 set, we just need to find Cachelines with the same 15 to 6-bit physical address. Secondly, to make sure eviction set locates in tile B's LLC size, we could use performance monitors in the reference 4 or the methods in work attack directory in the reference 5. More details could be found in our paper. If attacker on tile A accesses the eviction set we just described, tile A's L2 cache will load Cachelines from tile B's LLC, and then tile A's L2 cache will evict some Cachelines to tile B's LLC cache. This process will continue, and the attacker's match traffic will contend with the victim, just as the picture shows. We evaluate cross-core attack upon the inference of RC predicate. We could capture square or multiply operations or select window algorithm of dedicated multiple function. This function is used to encrypt or decrypt data by Java RC program. Like the picture in the right, the red point is the square operation we captured with a higher latency. The black star is a multiply operation, inferred from the gap. By an algorithm called SRID in reference 6, we could recover about 30% of all the RC predicates. That's all about cross-core attack. Let's introduce the cross-CPU attack. As the picture shows, we assume attacker controls one core on each CPU, and the victim will access remote memory. UPI is different from Mesh. Firstly, it contains a more complex traffic, so our monitors will be more cross-screen. Secondly, we have tested our evasion-based probe of cross-core attack, but we found it's hard to evade Cacheline to LLC on remote CPU. Instead, the copy may just drop if the lines are clean. So we use a different strategy. Our probe for cross-CPU attack is based on force sharing. Core A and Core B are on the different CPU sockets. They are connected by UPI. They will write the same cache lines as the picture below shows. And just one core needs to record the timestamps as the physical shows, according to the Cacheline coherent protocol, which is massive in Intel platform. Core A and Core B will compete for inclusive states of Cacheline to modify them. In this way, the cache lines are transferred between two CPUs by UPI. For evaluation, we use our core CPU attack probe to collect application and website fingerprinting. We collect traces of 40 applications and 100 websites. Then we train our LSTM-based classifier to classify them. For these two scenarios, the accuracy is about 80%. Here are some analyses of our work. For advantages, firstly, MeshUp does not depend on microarchitectural state chain. Attackers don't need to know the victim's memory addresses. Secondly, MeshUp could bypass current defenses against cache channel like Intel, CAT, and page coloring. The main limitation of MeshUp is that its attack granularity is low, because we could only monitor the data transmission of CPU interconnect data flow. We also did a little investigation upon the potential mitigations. The first direction is spectral isolation. As a graph, maybe we could deploy different virtual machines in different areas. The LLC slides are not shared between areas, and we should also improve the root policy to avoid cross-area mesh data flows. The second direction is cache randomization, like the LLC slides hash algorithm, because it will increase the difficulty of implement MeshUp attack. To conclude, firstly, we identify a new security implication of CPU interconnects. Secondly, we develop MeshUp to conduct cross-core and cross-CPU cache side channel attacks through CPU interconnections. Thirdly, we systematically analyze MeshUp and evaluate against RSA key recovery and application and website fingerprinting. Thank you for listening. Any questions?